Everyone, welcome back. So when we do that difference in electronegativity, we find that this first one is just barely inside that polar covalent, and nitrogen was the greater one, so the arrowhead's pointing towards there. The arrowhead always goes with the negative, tail end always goes with the positive. And then when we subtracted the electronegativity here, we fell in the polar covalent range again. Fluorine had the greater electronegativity, so the arrowhead points that way, and so that's our negative and our positive side. Okay, we need to draw Lewis dot structures. So when we do this, the first thing we do is count our valence electrons. So looking at the periodic table, boron has 3 valence electrons, and then chlorines have 7, and we have 3 of those. And so that would be 24 valence electrons. Then we decide what goes in the middle. Nature tends towards symmetry. We'll put that 4 on the middle. We start with single bonds to our remaining atoms, and there's 3 remaining chlorines. And then we're going to complete the octet for the outside. If we have any extra electrons, we'll put them as pairs on the center. So we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We've used all 24. Okay. Now this one, we would normally, if it wasn't boron, we would erase a lone pair and make a bonded pair. But because our center is either boron, beryllium, or aluminum, any of those, it's okay to have less than 8. That would be our suboctet. So we counted valence electrons, decided what went in the middle, started with single bonds, completed the octet for the outside atoms. If there was any extras, we'd put them as a pair on the center or pairs on the center, but we used all 24. Normally we would look at this and say, oh, 2, 4, 6, and erase a lone pair and make a double bond, but it's one of our 3 that it's okay to have less than that. So we have 3 domains. The 3D drawings that you're doing today on the quiz have the same number of domains. So you're not going to have the models available to you, but we'll have done them together just barely. And now this is a simple one as well, because it is 3 domains. It makes that trigonal planar, and so this can all be in the plane of the paper. Nothing is going in or out of the paper. So we show our angles really carefully here. Chlorine, chlorine, and chlorine. Again, I have the shape guide. It is on your quiz, the parts that you need, and so you don't have to have the separate sheet of paper. We said it was 3 domains, and it was 3 bonded atoms with 0 lone pairs, so that's where we get the trigonal planar for our molecular shape. Molecular geometry or molecular shape, okay, so not the electron geometry. That would be trigonal. Okay, trigonal planar. Now, we need to decide if the molecule is polar or non-polar. And part of that is the bond. So this is a bond between a boron and a chlorine. Oh, and we figured that out up here. We saw that the bond is polar, and it's pointed towards the chlorines. But is the molecule polar? Notice that we have symmetry here. Every single domain is the same. Every single one of these domains are all bonded chlorines. And so we have symmetry. So reminder, if it is symmetrical, then the whole molecule is nonpolar. But if it's asymmetrical, then the whole molecule is polar. So since we get that symmetry, every domain is the same, this would be a nonpolar molecule. All right, so let's look at one more together, and then I'm going to have you try one on your own. So we count our valence electrons. We'll get 10 valence electrons. Carbon can form the most bonds, so I'm going to put that one in the middle, and I'm going to start with single bonds to my remaining atoms. And we'll complete the octet for the outside. Hydrogens, they want just the duet, right? So we've completed this octet for nitrogen, and then hydrogen is good. We don't need to add those dots. If we have any extras, we'll place them as pairs on the center. So we've used 2, 4, 6, 8, 10. We've used all 10 again, so we don't have any extras to put on the center. So what we look at now is if our center has an octet or not. And it doesn't. Right now this carbon has 2, 4, and we need 8. And it's not one of the 3 that it's okay to have less than 8. So whenever you run into this, we need to erase a lone pair and turn it into a bonded pair. So this carbon now has 2, 4, 6. Okay, we're almost there, so we need to do it again. This one will be a triple bond. So what we end up with as far as Lewis structure goes, we have a carbon that has a triple bond to a nitrogen and then a single bond to a hydrogen. This atom only has 2 domains. It doesn't matter that it's a triple bond. It's bonded atoms off the center and lone pairs on the center. So we have 1 bonded atom, 2 bonded atoms, and no lone pairs. And so our model would be linear. And so that's, again, all in the plane of the paper. So we have a carbon bonded to a nitrogen, bonded to a hydrogen. When we draw our 3D shapes, we don't have to show lone pairs on the outside atoms, and then we don't have to show if it's a single, double, or a triple. And like I told you before, your reference will be available to you. It's on the quiz. So we have 2 domains, and it's 2 bonded atoms with 0 lone pairs, so the molecular shape is linear. So when we're saying molecular geometry, think molecular shape. Okay, if we consider the bond, a bond between a carbon and a hydrogen we already said was nonpolar. But the carbon and the nitrogen is polar, and it's pointing towards the nitrogen. So there's 2 domains, but they are not the same. And so that would give us that asymmetry. Since they are not the same, this would be a polar molecule. Okay, I want you to hit pause, take a couple minutes, and complete this one, and then check back in with me, and let's see how you did. So our Lewis dot structure, we counted 42 valence electrons, so we have a pair of a lone pair on the center. This is an expanded octet. And this is what our model would look like. We have 6 domains. And so this one, we think of our plane of our paper. Let's get that like X shape there. That would be in the plane of the paper. And then we have one that's coming out towards us, and then we got a lone pair that's hiding underneath there that's going into the paper. So we have our iodine bonded and in the plane of the paper to 4 fluorines in that X shape. And then we have one that's coming towards us, so that's our solid wedge. It's a fluorine. And then the lone pair that's going away from us into the paper, so that's our dashed wedge. Okay. Reminder, when it's 5 domains, it's very similar to this, but instead of 1, 2, 3, 4, we have like a trigonal plane, or we get a triangle in the middle, and then one going out, one going in. So back to our molecular geometry, we have 6 domains, and 5 of them are bonded atoms, 1's a lone pair, so we're going to get a square pyramid. Or square pyramidal. It's asymmetrical again, because if this was a fluorine, it'd be symmetrical, but one of the domains is different than the other ones, and due to that asymmetry, you get a polar molecule. Okay, last concept. We have to read this graph backwards. So this is distance, and this is energy. So think of it, this image part's not my favorite. Think of it like we have one atom here, and then we got one over here that we're going to bring closer to it. Okay. Okay, so do you remember this interactive that we had? So we have these 2 atoms. I'm going to bring this one closer to it. And as I bring it closer and closer, The energy is lowering, and look, we're getting an attraction that's increasing in between them. Okay. And then we get to this ideal location, and energy is the lowest, it's balanced. The attractive force is equal to the repulsive force. But if I cause them to be closer than this like perfect bonding length, then the energy shoots up drastically. And look at that repulsive force. It becomes huge and quickly. Oh, I can't drop the object there. And so then if I let go, it goes back to that ideal distance away. Okay, so let me pull up the camera again. Repulsive force causes energy to increase. That happened right here. The nuclei of this atom got way too close to the nuclei of that atom, and the repulsive force made that energy shoot up. We had, when there was no overlap, like no attraction, they were so far away from each other. That happened right here. When the attractive force was stronger than the repulsive force, when we saw that attraction increasing, that's when the energy was lowering. And then we got to this lowest energy, most stable state. And that distance between them, that distance is the bond length. Make sure on the quiz, conceptually, you're going to need to be able to describe each of those. Okay, so keep an eye on the clock. I want you to take a moment, talk to your inquiry partner, answer any questions you have about this, talk through it, and then once you get to make sure that you are working on this quiz, giving yourself 20 minutes to complete it, and we'll turn it in at the end of class. Okay, make sure your name's on it and turn it in. Okay, thank you guys. Thank you for your hard work. We will grade it next class.